Hi there. Welcome back to Weather Analysis with Mr. CB. We're going to talk about the upper atmosphere now. So we were just talking about the skew log P. That's pretty much all we're going to talk about for this point. So now, to recap on that a little bit, we learned about, what are those background lines on the skew log P? What are the lines that get added by the radiosonde, those two lines, and how can we draw a parcel trace to expect or see what we would expect a parcel of air to do at certain points in the atmosphere. And then how can we use certain intersection points in areas to help us know where, amount of energy needed to lift or potential for thunderstorms. But now we're switching gears and we're going to just talk about the upper atmosphere. So in the upper atmosphere, we have station models just like we do at the surface. Um, and I did not actually, well, I don't remember if I did or not, but I don't think I'd talked about the station models for the surface. So that might be something to brush up on if you don't know what that is. But that's these things here, and there's four different things around it. But we also have that in the upper atmosphere, and the four things are we have TT, DDDD, HHH, and PP. So the TT, that's going to be on the upper left of this model. This is the temperature in Celsius, in degrees Celsius, that would be at that height. The DDDD, that's the dew point depression in degrees Celsius. So careful, it is the dew point depression, not temperature. The HHH is a geocoded or coded geopotential height. So it's basically telling us a height, but it's coded so that why we call this HHH is because there's three numbers that are going to happen for this. So just like how we have sneaky things with the pressure where, oh, if I see these numbers on the station model, oh, I'll know that you'll do this or that to get the actual pressure. Same thing for the heights. We're going to have a three-digit number and it's going to be something in the 900s or in a zero or in the zeros. I don't know if you'd really say that, but a zero first. Now, if you have a number that starts with a nine, so let's say 975, that is decameters. That's the unit that we use. And the reason why we use that instead of just meters is because we would have too many digits and we just don't need that clutter on the map. But if you want to know what it is in meters, just add a zero at the end. So it'd be 9750 meters. But if you have a number that starts with zero, which can also happen, you put a one before the zero and a zero after at the end. So if you saw 031, it really means 10,310 meters. And then the PP that's on the bottom right is just a 12-hour height change. I'm not going to really talk about that right now. All right. Here is a map showing what I just talked about. It's kind of glitchy, so sorry about that. But how do we know this is in the upper levels? Well, that's because of this. See, sorry. See that 300 HPA? That really means 300 millibar. So this is a 300 millibar pressure map. What does that mean? Everywhere on this freaking thing is 300 pressures, or sorry, 300 millibars. I'm kind of tired. 300 millibars, and um, we have changing height on the map. So when we're looking at a surface map, it's the same height everywhere, which is the surface, and the different areas on the map are different pressures with isobars. But now, anytime we are in the upper levels, instead, it is a map of constant pressure with differing heights. And we've already talked about this before. But you can see on this map those four different things that we were talking about. And let's just look at this one that's circled. You see that 048, that's really going to be you put a one at the beginning and a zero at the end, so it's 10,480 meters. and it looks like negative 33 degrees Celsius um temperature. And then the wind flags are still the same as they are for the pressure. They still mean the same thing. So the number of flags indicate knots, and the direction that it's pointing is the direction that it's coming from. So right here, that means it's pointing this way, so the winds are coming from the southwest. All right, the different levels that are included in the upper level atmosphere and what they mean. We can have a 200 millibar level used in the summer, 250 in the fall, spring, and 300 in the winter. All right, if we have an upper level low, what does that mean? That's going to be where there's a trough, and that means height is low, not pressure, because once again, the map is of constant pressure, but differing heights. So a low on these maps, instead of it meaning low pressure, it's going to mean low height. So that means to get that pressure, which might be 300 millibar, for example, you have to go to a lower height to get to that pressure. That's what that means. More height changes are expected since there's a fall equinox. So right now, you might be watching this at a different time of year, but right now it's September, um, almost October. And once we get to this time of year, there's going to be a lot of height changes that we start to get that. It's more constant in the summer, but once we get into this fall equinox, that changes. Um, we can say the trough or ridge is positively or negatively tilted based on the tilt of it, obviously. And so we also have a jet streak. And there are jet streaks within the jet stream. The jet stream is basically a stream of flowing winds. And there's going to be ridges and troughs associated with that, but a jet streak within that jet stream is the corridor of the fastest winds. All right. Now, in the upper atmosphere, we have troughs and ridges. I already talked about this. But if we have a trough, that means that there are lower heights. There's a decrease in thickness of the atmosphere. And the reason why that is that it's colder, mean temperatures. And in the troughs, we have compression. Ridge is going to be where there's higher heights, increase in thickness, and that's because of warmer mean temperatures, and there's going to be expansion in that case. I already talked about what the jet stream is, so I'm not going to say that again. Horizontal temperature differences are going to influence the horizontal pressure differences. We'll talk more about that later. Um, so the magnitude of the forces that we have is going to increase for a greater change in height. The movement is still going to go from high to low. It doesn't matter that we're not talking about pressures now. We're talking about heights, but still high to low is going to be what happens. And the left of the wind flow is going to be where there's lower heights. Just be careful of your point of view. You have to think about what direction the wind is going, and it's the left of that, not just the left of the way you're looking at the map. Um, the general flow of winds that we're going to have is going to be from west to east, and we call that westerlies because winds are named about they're named based on where they come from. So if we're going from west to east, that's why we call it westerlies. If we were going from east to west, then it's easterlies. But in these mid latitudes, such as the United States, that this course is mostly based off of, we we'll expect the general flow to be from west to east. Um, you can see in this uh, graph, or not graph, model, if you want to say, how I was talking about if there's a greater change in height, the forces increase. You can see here is 800 or 18,000 feet. Here's the surface. Well, here there's the biggest change in height, and the forces magnitudes are larger, indicated by the longer arrows. So Coriolis, remember Coriolis and pressure gradient force are going to be the two primary forces that there will be. We already talked about those before, so review that if you need. But if the ISO heights are closer together, we have faster winds, just like how if we have pressure lines close together. Now, we can use what's happening in the upper atmosphere to help us know what would happen at the surface. So where the most divergence um, is where the low will be. And, you know, that's not going to be directly uh at the trough in the case of the low, and for the high, it's not going to be directly at the ridge. Remember my analogy about convergence and divergence. For divergence, we'll think about the speeding son or grandson with the grandma left behind. He speeds ahead, their car separates, so faster winds ahead of the slower winds, and then she's like, "Oh, wait up." That is going to be divergence. And if we have divergence, you can see right here, then there's a gap created. To fill the gap, air rises from below. Well, since that happened, the mass decreased at the surface. Oh, since that happened, low pressure at the bottom. So as you can see, the low pressure is not going to be directly below the trough. It's going to be where directly below the divergence. And the divergence is always going to be just after the trough because at the trough, um, things have been slowed down, but they're starting to pick up like the sun speeds off, but the grandma's left behind. Convergence, other way around, you have this slow grandma in the front, so the slower winds ahead of faster winds, and the faster winds like the someone that crashes into the back of the slow grandma, that convergence is going to cause air to go be pushed down, sink, and now there's increased mass at the surface, and that means higher pressure there. And once again, that's not right at the ridge, it's right after it. Review the other video if you don't remember that. All right. And that's going to be it for this video. Thanks for watching. As a side note, I'm sorry if this video was slightly lower quality because it is 1:50 a.m. when I'm recording this. I'm pretty tired, and I know that there was like a couple moments when I kind of lost my train of thought. So sorry about that. But thanks for watching.